let's do this one. The half-life of a radioactive substance after 1 year. The half-life of a radioactive substance. Oh, sorry. Find the half-life. I missed an important word there. Find the half-life of a radioactive substance if after 1 year 97% of it remains. And we're supposed to use the idea here that the amount of radioactive substance let's call that Y is proportional to the rate of change of the amount of substance. This is a very long way of writing out the following differential equations. So we've got this whole setup. Now I will say radioactive decay and exponential growth are problems you could totally do without using a differential equation. But that's not really the point, so we're going to use differential equation. But you totally know that the model is going to be like y equals c to the kt. We're still going to do it the long way. So here's kind of the really important piece of information. Y is proportional to the rate of change of the amount of the substance. Sorry. The amount, yeah. Right. So we can say that dy dt is equal to k times y. They're proportional to each other. That means one thing multiple of the other. So this is the differential equation that is saying. And I will say people often say it the other way. People often say that the rate of change of the amount of stuff you have is proportional to how much stuff there is. But you can say the proportional part either way. So that's our differential equation that we're going to try and solve. Now, we can solve this in a couple ways. Well, maybe not a couple ways. The usual way of solving this is to separate the variables. I suppose you could, there are other methods, but usually if you can separate variables, you want to. So when I see dy dt over here, I know that the y's have to end up on that side and the t's have to end up on this side. So if you ever have a derivative of one side, the variable that's on top has to stay on that side and the variable that's on the bottom has to end up on the other side. So I'm going to multiply both sides by dt and divide both sides by y. So then I get 1 over y dy equals k times dt. I could have put the 1 over k here as well. I don't really want to. You don't want to either. So we've separated the variables. All the y's on one side, all the t's on the other side. The constant also on the other side. And now, we're going to integrate both sides. The integral of 1 over y, as we've learned, is the natural log of, well, it's the natural log of the absolute value of y. Do we need the absolute value? Maybe. And on the other side, we get k times t plus c. Okay, so now I have to solve for y. So I'm going to exponentiate both sides. I'm going to get e to the natural log of the absolute value of y. What's e to the kt plus c? What happens here is that I get the absolute value of y equal to e to the kt times e to the c. E to the c is just a constant, so we call it c again. People call it a different name. People often call it the same name. So this is just a constant. So we're going to call this c and say, oh, look, I really got absolute value of y equals c e to the kt. Now, in this particular problem, y is always positive. So I can drop, right, because we're talking about the amount of stuff, which is never negative. So in this case, you can drop the opposite values. Sometimes it's more of a question we have to actually look at. So not surprisingly, we've got a radioactive decay problem, and we're looking at the model y equals c to the kt. This is really how we get there, right? When we did this before, like in Calc 1, there's like, oh yeah, y equals c to the kt. Someone in the background was like, oh yeah, really there's this differential equation that we're solving because we're starting with this differential equation and saying, oh, this is actually the solution to that differential equation. The rest of the problem is just algebra. Not that we shouldn't do it, but it is just algebra. So the rest of the question is, so we know that at the beginning there's 100%. So, right, times 0, there's 100%. And then time 1 year later, there's 97%. So we can use this stuff to find what the stuff. Well, that's a good question, Mariah. I think if you know it's exponential growth or decay specifically, you can probably just jump to the y equals c to the kt. The issue is there are other differential equations that don't always work out so nicely. So that's why it's good to still be aware of the process for solving a differential equation. But yeah, so here then we're going to do, y equals 100. I'm just use 100 instead of 100% e to the kt. Plugging in 100 for y and 0 for t gets me 100 for the c value there. And then I plug in 97%. So 97% of 100 is 97. Equals 100 e to the k times 1. Divided by 100, you get 0.97. Not surprising, that's 97% as a decimal. Equals e to the k. Take the natural log of both sides. So k is equal to the natural log of 0.97. So now we've got our model. Our model is y equals 100 e to the k times t. Now the question is, what's the half-life? So to figure out the half-life is, we're going to set the amount of stuff we have to be half of what we started with. So I'm going to set y equal to 50 and solve this equation. So 50 equals 100 e to the natural log of 0.97 times t. Divide both sides by 100, you get 1/2 equals e to the natural log of 0.97 times t. Take the natural log of both sides, get the natural log of 1/2 equals the natural log of 0.97 times t. Divide both sides by that, and you get t equal to the natural log of 1/2 over the natural log of 0.97. So that's how you, most of these word problems, usually, not always, but a lot of the times, are kind of boiling down to being some sort of exponential growth or decay kind of problem. Even if it's a, well, so it's a good question. Here's the thing. K is negative. What's a negative number? Some people, when they do this, they like to write it as y equals c e to the negative ket. I am not a fan of that. It's fine. It works fine. If you like doing it that way, it's really okay. But I think it's an unnecessary kind of extra thing that just kind of reminds you that it's a negative thing, but it's not really helpful at all. So yeah, if you're taking the natural log of something that's less than 1, that's going to be a negative number. So let's look at solving a couple other differential equations, which is really just going to be integration, and then we will move on to something else. So we could ask the question to maybe solve something like the following differential equation. dy dx equals, that's really raining outside, 3x squared e to the negative 4y. Okay, so what variable has to end up on the left? X's or y's? Whatever's on top. Whatever's on top of the derivative has to be the thing that ends up on that side. So y is on the left, x is on the right. So I'm going to divide by e to the negative 4y. Right, this is dy over e to the negative 4y equal to 3x squared. I'm going to bring the dx over. And then before integrating, I would probably do one more thing. I'd probably rewrite this as e to the 4y dy equal to 3x squared dx. I'm going to simplify this thing here so that it's relatively easy to integrate. Okay, so now I'm going to solve, well, I'm going to integrate. Integral 3x squared is just x cubed plus c. You can put the c on either side, but we almost always put it on the side with the independent variable. So if we're thinking of y as a function of x, which we definitely are because we've written the derivative in the way where y is depending on x, then we're trying to solve for y. So we want it to be easy to solve for y, so we're going to put all the extra junk on the other side. Okay, so what's the integral of e to the 4y? That's a good question. It's almost e to the 4y, except the derivative of e to the 4y is e to the 4y times 4. The integral of e to the 4y is e to the 4y divided by 4, or times 1/4. So great, there's our integral. Now we're going to solve for y. So I'm going to multiply both sides by 4. I'm going to get e to the 4y equal to, normally I would write c, but I'm going to do it slightly differently to show you c. So I'm going to call this c1. When I multiply both sides by 4, I'm going to get 4x cubed plus 4 times c1, which I'm going to call c2, a different constant. It's 4 times c1. And then I'm going to take the natural log of both sides. So 4y equals the natural log of 4x cubed plus c2. And then divide both sides by 4 or multiply both sides by 1/4 and get y equal to 1/4 the natural log of 4x cubed plus c2. But I'm just going to call it a constant. So really, when I multiply a constant by a number, right, that's really 4c1, or add to a constant or subtract from a constant, I usually just call it the same thing. It's pretty standard. So there's your answer. If you took the derivative of this, not that I'm going to, but if you took the derivative of this, it would be equal to 3x squared times e to the negative 4 times this. It's kind of funky, but it would be. Yeah, cool. At this juncture, in fact, actually in this whole class, almost all of the almost all of the differential equations we encounter are separable. So the first problem we did was like, do you have an example of one, Morgan? Because I feel like the first problem that we did was kind of like taking a word problem and writing a differential equation. I don't know if I have any other really like challenging examples. I can look at the book, I suppose. Let me take a look. One sec. Okay, there are some interesting examples here. Oh, yeah. Sorry. Let me continue with these differential equations, and then I'll swing back around to trying to come up with one that is more of a word problem. So let's look at the following one. I've got cosecant of x times dy dx equal to e to the y plus cosine x. And again, as I was saying, I think in this class, pretty much every differential equation we're going to encounter is of this separable variety, which is nice because they're pretty straightforward. When you take 22B, which is an actual differential equations class, then you'll learn more about all the other differential equations that you can see. And there are lots of types of differential equations and many ways to solve them. But for this one, again, I'm just going to separate. So first, the only operations that we are really allowed to use to separate things, to get the y's on the left and the x on the right, is either multiplication or division. That's kind of it. So I need to figure out how to deal with this. I need to rewrite this as cosecant of x times dy dx equal to e to the y times e to the cosine of x. So now I can, let's say I'm bringing the x's to the right, the y's to the left. So I can divide by e to the y. You have 1 over e to the y dy equal to, I can multiply dx, and I can divide by a cosecant of x. Now, as is, this looks like it might be kind of hard to integrate. I definitely need to do some rewriting. I should definitely rewrite this as e to the negative y dy. And dividing by cosecant is the same thing as multiplying by what? Right, cosecant is the reciprocal of sine. Sine, definitely not cosine, it is just sine. So cosecant is 1 over sine, secant is 1 over cosine. So you get sine of x times e to the cosine of x dx. And now we're going to integrate both sides. And just so you guys are aware, whenever you integrate e to the something times x, you get e to the something times x divided by that something. Because the derivative of this is e to the ax times a, and the a times the 1 over a cancels out. So integrating e to the negative y, I get e to the negative y divided by negative 1. But divided by negative 1 is the same as multiplied by negative 1. So I'm just writing negative e to the negative y. On the right-hand side, I'm going to, on the right-hand side, what am I going to do? I think I'm going to have to do a U substitution. I can let u equal, all right, here's a good question. Should I let u equal sine or should I let u equal cosine? Definitely cosine. Sine feels like it might be a better choice because like the derivative of sine is just cosine, the derivative of cosine is negative sine, but cosine is the thing that's stuck inside another function. So u is cosine of x, and my du, the derivative is negative sine of x dx. So negative du is positive sine of x dx. This pen is trash. So this is going to end up being the integral of sine of x dx is negative du, and then e to the u. That's a u. So I end up with negative e to the negative y equal to negative, the integral of e to the u is e to the u plus c. So I really have, up here. So what I really have is negative e to the negative y equals to negative e to the u, which I just erased. U was cosine of x. Plus c. So now we're going to try and solve for y. So I will point out it's not always going to be possible to solve for y. Most of the time it will be though. So I'm going to multiply both sides by negative 1. So I'm going to have e to the negative y equals e to the cosine of x. A constant times a negative 1 is still a constant, so I'm still going to write plus c. And then I'm going to take the natural log of both sides. The natural log of e to the negative y is negative y. The natural log of all this, it would be lovely if it was just cosine of x, but that plus c actually kind of jams up our stuff here. It's the natural log of e to the cosine of x plus c. That c is kind of throwing off what would be a very nice answer. So our final answer is y equal to negative natural log of e to the cosine of x plus c. And there's nothing we can do about that other than say that that's our answer. Kind of disappointing. All right, let's do one more of these type, and I'll try and see if I can identify a word problem that isn't too terrible. Okay, here's the last one I have here. Let's say we've got dy dx again equals y natural log of y over 1 plus x squared. This one's a little different. We also have an initial condition that y of 0 is equal to e squared. E squared? E squared. Okay. Same thing we've done the previous few times. All the y's come to the left, all the x's go to the right. This is going to be 1 over y natural log of y. I'm dividing by y natural log of y, dy, equal to, I'm going to multiply by dx. I'm going to have I could write dx over 1 plus x squared. I'd rather write 1 over 1 plus x squared dx. Yes, I know I wrote the integral already, getting ahead of myself just a little bit. So there we have it. We multiply both sides by dx. We divided both sides by y natural log of y. And now we are going to integrate both sides. On the left side here, we're going to do a U substitution. U is the natural log of y. Du is 1 over y dy. Well, great. I've got a 1 over y dy. So that's going to be my du. So this left-hand side is going to be the integral of 1 over u du, which is going to end up being the natural log of the absolute value of u, which is going to end up being the natural log of the absolute value of the natural log of y. No absolute values on that one on the inside. Kind of funky. The right-hand side, what's the integral of 1 over 1 plus x squared? Everyone's favorite inverse trig function. Arc tangent of x. All right, so here's what we plus c. So here's what we've got. We've got natural log of the absolute value of natural log of y equal to the arc tangent of x plus c. Now, this brings up a good question. When do I want to solve for c? Do I want to try and solve for c now? Maybe. I could. If I solve for c now, I plug in 0 for x. An arctangent of 0 is 0. I plug in e squared for y. Natural log of e squared is 2. Natural log of 2 is natural log of 2. So I'd have c equal to natural log of 2. The problem with that is now I have to carry that the whole way through, and I might not actually want to do that. So while I could, so if I exponentiate both sides, if I do e to the this equals e to the that, e to the natural log of some stuff is just the stuff, so I get the absolute value of natural log of y, equal to e to the this is e to the arc tangent of x plus c. Now, I could say that c is natural log of 2 like we found it to be, and then break this apart and say e to the arctangent of x times e to the natural log of 2, which is just 2 times e to the arctangent of x. I would rather not find that yet. I would rather just kind of carry this and treat it kind of abuse it actually. So I'm going to rewrite this as e to the arctangent of x times e to the c. And then I'm going to call e to the c a new constant. Which we usually call c because we're lazy, because we can't think of a new letter. You can call it something different if you want. Okay. And now we're going to do it again. I should point out that we can drop the absolute values at this point because e to the anything is positive. So we can get rid of those. So then I'm going to e both sides again. Well, that seems weird. All right. Here's what I've got. E to the natural log of y is y. And I've got e to the c times e to the arc tangent of x. That looks terrible. However, you might play with this, you might not. I think I don't want to play with it. I want to figure out what y is now, or I want to figure out what c is now. So remember, this c is not the same as that c, or that c. So I'm going to plug in 0 for x, e squared for y. So get e squared equal to e to the c times e to the arctangent of 0, which is 0. C times 0 is 1, so e squared equals e to the c, so my c is equal to 2. So one way I could write this answer would be that, somewhere I have room, would be y equal to e to the 2 times e to the arctangent of x. Which seems like a very strange answer. Kind of bonkers. There are questions about this question. Okay, let's look at another. Oh, can you just stay there for a minute? Oh yeah, sure. Let me erase the other side. Let's see, there was something else I wanted to see real quick here. Where'd my notes go? There'd you go. Okay. All right. Sure, let's do this one. Okay, I don't want to write this all down because it gets kind of long. So I'll read it to you guys and then we'll talk about it. So police discover the body of a murder victim at 10 p.m. Body, 10 p.m. At the time, the body temperature is 87 degrees. 1 hour later, it's 86 degrees. The room temperature is 70 degrees. So the room temp is 70 degrees. And the normal body temperature of a living person is 98.6 degrees. So normally 98.6. Assuming, so this is the part where we actually have to listen to the words to write the differential equation. Assuming that the rate of change in body temperature is proportional to the difference of the body temperature and the temperature of the surrounding environment, estimated at the time of death. Okay. So let me read that again. Assuming that the rate of change of the body temperature. So let's say capital T is body temperature and little t is time. So the rate of change of body temperature, dt is proportional to, so it's some constant multiple of, the difference in the body temperature and the temperature of the surrounding environment. So I'm going to say T is the body temperature and the surrounding environment temperature is 70 degrees. So this is how we set up the differential equation here, right? We have d dt equals k times T minus 70. Rate of change of the body temperature is proportional to the difference in the body temperature and the surrounding room temperature. I will also point out that if you knew the equations for Newton's law of cooling, which come from this differential equation, you could totally bypass this part. I still think you shouldn't, right? It's worth doing this, but this is a Newton's law of cooling problem. So now I want to know what time the person died. All right, so I need to solve this differential equation before I do anything else. So I'm going to separate my variables. I'm going to divide both sides by t minus 70. So now dt over t minus 70. And multiply both sides by little dt. We're going to integrate both sides. Integral of 1 over t minus 70 is the natural log of the absolute value of t minus 70. Integral of k is kt plus c. So then we exponentiate both sides. We get e to the natural log of stuff equals e to the stuff. E to the natural log of the absolute value of t minus 70 is the absolute value of t minus 70 equal to, I'm going to write this as e to the kt times e to the c, which is just going to be a new constant. Like that. And then, so then you have to ask yourself, and this actually is kind of interesting, is the stuff inside here positive or negative? Well, since the body started off warmer than the room, the stuff inside here is positive, right? The body's never going to get to be colder than the room. However, if the problem was you put a cold beverage in a 70-degree room and you were trying to figure out, right? And so let's say it was the same situation, except the now temperature is representing the temperature of a cold beverage that you put in a 70-degree room. If that was the case, here's what would happen next. You'd have to say that negative t minus 70 is equal to c to the kt. Because the insides are negative if the temperature is less than 70 degrees, but the absolute value has to make it positive. It's not that big a deal, and you can usually just kind of fix it. Really what people do, to be perfectly honest, is they totally ignore the absolute values, and they just say, oh, I'm just going to pretend like c can be positive or negative. So if it needs to be negative, I'll really just throw the negative sign on my c. If c needs to be positive, great, works out. So really what I should be saying to all of you is you can pretty much ignore these absolute values when you're solving these differential equations. That is the real truth of the matter. All right, so here's our equation. I don't want to erase anything important. I guess I'll go to the other side here. Don't worry, I'll go back to the other side in a sec. So our equation for the body temperature at some time is temperature at some time minus 70 degrees equals c e to the k. And we know, so here's what I'm going to do. I'm going to say 10 p.m. I'm going to call time equal to 0 10 p.m. The body temperature was 87 degrees. And 1 hour later at 11 p.m., when time is 1, the body temperature was 86 degrees. I can use these two pieces of data to solve for c and k. And then I can use the final equation to figure out when the body was 98.6 degrees. Okay, so I'm going to plug in 0 for t and 87 for capital T. So t of 0 is 87 degrees, so I get 87 minus 70 equals c e to the k times 0. 17 equals c e to the 0 is just 1. So 17 is equal to c. And then the other thing, we're going to plug in time equal to 1 hour and temperature equal to 86 degrees. So then 86 degrees minus 70 equals 17 is c e to the k times 1. And now I can solve for k. 86 minus 70 is 16. 16 divided by 17 equals e to the k. So natural log of 16 over 17 equals k. So now I've got the model. The model is the temperature minus 70 degrees equals c, which is 17, e to the k, which is natural log of 16 17ths. Now what we have to do is plug in 98.6 degrees for temperature and solve for T, time. And I guess I can erase this now since I'm kind of with it. So plug in 98.6 for temperature. 98.6 minus 70 equals 17e to the natural log of 16/17 t. Subtract, you get what? 28.6. Son of a gun. Really don't love getting black marker on the carpet. Oh wow, that's life. I'll clean it up later. I'm going to destroy this carpet if I'm here for much longer, which I will be, so I guess I'm going to destroy the carpet. All right, anyway, sorry, not important. So this is 28.6 divided by that equals e to the natural log of 16/17 t. Take the natural log of both sides. The natural log of 28.6 over 17 equal to e. The natural log of e to the stuff is just the stuff. And then finally divide by this, so that t is equal to this gross thing, natural log of 28.6 over 17, divided by this gross thing. Now, before we even calculate this, you might notice something. The top logarithm is definitely positive, right? Because 28.6 divided by 17 is bigger than 1, and the natural log of a number bigger than 1 is positive. But this bottom logarithm is going to be negative. So when we divide these, we're actually going to get a negative time. Let's see what we get. Natural log of 28.6 divided by 17 is 0.5-ish, divided by the natural log of 16 divided by 17 ends up with negative 8.58. Let's round up to negative 8.5. So the time of death is about negative 8.5 hours. Now remember, and I probably shouldn't have erased it, but I did. On our time chart here, right, time equal to 0 was 10 p.m. when the body was 87 degrees. 8.5 hours before that is going to be, well, let's see, negative 8.5 plus 10 is 1.5. So at 1.5 p.m., the body was 98.6 degrees. So about 1:30 p.m. is when this person was no longer living. And it's kind of a gruesome example. I mean, not really that gruesome, but okay. So again, the algebra here, not super important. I mean, it is important, but not the most important. The important part here is really, oh yeah, we're able to set up this differential equation by understanding that the rate of change of body temperature is proportional to the difference in the temperature and the room temperature. So that's really, right, when they say the rate of change of something is proportional to something else, you should be thinking, oh, rate of change is derivative proportional to constant multiple times the thing they're trying to describe. Okay. What now? I think we should do a couple. The problem is, I can spend the whole rest of the class talking about trig intervals, but I feel like we should definitely get to integration by parts today. So let me do a few trig examples. I'll do some sine and cosine ones, and then maybe next class we'll talk about secant and tangent ones. So let's go this way. And then we'll get to integration by parts, and we can do some double integration by parts. Sure. So trig examples. There's kind of three varieties of powers of sines and cosines and powers of secants and tangents. So let's say I have the integral of, and we're going to start off hard. Okay, we're going to start off hard. Integral of cosine squared of x. So when you're integrating powers of sine and cosine, if all the powers are even, you have to use the half angle formulas. So the half angle formula says that cosine squared of x is equal to 1 plus cosine of 2x all over 2. And the half angle formula for sine is very similar. Sine squared of x is 1 minus cosine of 2x over 2. And what I always remember about these formulas is if you add them together, you get 1. Because if you add them together, you get 1/2 plus 1/2. You get a plus cosine of 2x over 2 and a minus cosine of 2x over 2, which cancel out. So you get 1/2 plus 1/2, which is 1. Which makes perfect sense because cosine squared plus sine squared is definitely equal to 1. So it's kind of a nice reminder that if you're not sure about these formulas for cosine squared and sine squared, if you write them down and then think about adding them together, if they equal 1, you've probably written them down right, unless you've switched them. I just remember the cosine one is plus because, I don't know, it's a cosine here, it's a cosine here, it should be positive. It's not really a good reason, it's just how I remember it. So I'm going to rewrite this as the integral of that. 1 plus cosine of 2x over 2. Which I would rather really write as 1/2 times the integral of 1 plus cosine of 2x. Okay. What's the antiderivative of 1? X. Let me ask you a slightly different question. What's here? What's the antiderivative of cosine of just x? Everybody, it's like, I don't want to say anything. It's sine of x. Okay, so is the antiderivative of cosine of 2x sine of 2x? It doesn't feel quite right. If I took the derivative of this, the derivative of this would be cosine of 2x times the derivative of 2x, which is 2. But I don't have a cosine of 2x times 2, I just have a cosine of 2x. So this is another example of, I know I said this way back when, this is an example of what I call a mini U substitution, where we could do u equals 2x and du equals 2dx, whatever. But basically, if you're integrating something, instead of it being a function of x, it's a function of a multiple of x, you end up dividing by that multiple of x. Which I would probably write as 1/2. I would really write this as 1/2 x plus 1/2 times 1/2 is 1/4 sine of 2x. Let's see. So whenever you have even powers of sine or cosine, or combined sine and cosine, or you have cosine squared times sine squared, which is terrible, you have to replace each of them with their half angle identities. But sometimes you have not quite that horrible situation. Sometimes you might have something like the integral of cosine x times sine to the 4th of x. So here is your intuition. Whenever you have an odd power of one of these trig functions, sine or cosine, and an even power of the other, you always want to let u equal the trig function all by itself that happens to be raised to the even power. So I know I want to let u equal just sine of x, which seems reasonable, right? My du is going to be the derivative, which is cosine of x dx, and I exactly have a cosine of x dx. Seems like the perfect choice. So then we're going to rewrite this as the integral of, let's see, so that's my du, and I'm left with a u to the 4th. So integrating that, I'm going to get u to the 5th over 5 plus c, and then u is sine of x, so it's sine to the 5th x over 5 plus c. Sorry, what's that? Sorry, it was kind of weird noise. So it's fine though. No one's. We're not. It's not 1:30. We're not going to find my body. So everything's okay. The doors are locked. Anyway, plus it's 2:30, right? So I'm fine. I'm safe. So let's look at this next one. Let's look at sine cubed x cosine to the 4th x. Similar situation, but it's going to be a little bit more challenging. So in this problem, we're still using the same idea. I want to let u equal the trig function. I should say, I want to let u equal either the sine or the cosine that's raised to the even power. If there's an odd and an even power. So u equals, oh, yeah. So u equals cosine x. Why am I picking cosine? Well, there is a reason. The reason is I really want to pick the thing that's not to the odd power, because when I find the derivative of cosine, the derivative of cosine is negative sine. And that's going to take care of one of these signs. And I'm going to write this as negative d equals positive sine of x dx. So watch me rewrite this. I'm going to rewrite this as the integral of, well, sine cubed is sine squared times sine. So write this as sine squared of x times cosine to the fourth of x times sine of x dx. I've still got the same amount of signs. But now, sine of x dx is negative du. So I can start rewriting this as negative the integral du. And I want you guys to tell me, what's cosine to the fourth going to become? Anybody? Anybody? I feel like closing doors very loudly. All right. Well, you guys outweighted me. I guess I'll just tell you. So cosine to the fourth is cosine of x to the fourth power. Cosine of x is u. So that's going to be u to the fourth. The real question, though, is what the heck am I doing with the sine squared? So here's why we picked u equal to cosine and not equal to sine. I picked u equal to cosine because there were an odd number of signs. The derivative, the du, ate up one of those signs. And an odd number minus 1 is an even number. So eating up one of those signs left me behind with an even number of signs. And I know a trig identity for any even power of sine. It's not the one we just used. It's the fact that sine squared x plus cosine squared x equals 1. So that sine squared x equals 1 minus cosine squared x. But cosine of x is equal to u, which is equal to 1 minus u squared in this problem. So this is going to become u to the fourth. This is going to become 1 minus u squared. Yeah. So then we can rewrite this integral as negative the integral. I have to multiply it out. I have to distribute the u to the fourth to each term. So it's negative the integral of u to the fourth minus u to the sixth du. We integrate. We get negative u to the fifth over 5 plus, minus u to the seventh over 7. Ow, son of a gun. Ow, that kind of hurt. And then finally plug back in that u is equal to cosine. So I end up with negative cosine to the fifth x over 5 minus a minus is plus cosine to the seventh x over 7. So that's how we deal with these problems. If you have sine and cosine and one's to an odd power, one's to an even power, you always let u equal the trig function sine or cosine that is to the even power, so that your du will take away 1 from the odd power and you'll be left with something you can deal with. Okay. So when one even and one odd power is kind of the case where you have to be the most careful, because you have to actually let u be the thing that is easier to deal with. So let's look at when they're both odd powers. Let's have the integral of cosine to the seventh of x times sine to the fifth of x. I want to change that. Let's make it sine cosine to the fifth, sine to the seventh. In this problem, you can let u be either trig function, sine or cosine. Doesn't matter. typically it is going to be easier on your life if you let u be the one that's to the higher odd power. So I'm going to let u equal sine of x. Du is equal to cosine of x dx. So here's what I'm going to do. I'm going to rewrite this. This is going to be cosine to the fourth x, right? Breaking off one of the cosines, times sine to the seventh x, times cosine of x dx. All right. Sine to the seventh is going to be u to the seventh. I really, really, really want to stress. Cosine to the fourth x is not 1 minus sine to the fourth x. Instead, we have to work a little harder. So I want to say, right, cosine to the fourth x plus sine to the fourth x. Not 1. Not generally. Sometimes maybe, but not always. But I know that cosine squared x plus sine squared x equals 1. So that cosine squared x equals 1 minus sine squared x. But sine x is my u. So cosine squared x is equal to 1 minus u squared. And then if I square both sides, cosine squared squared, which is cosine to the fourth, is 1 minus u squared squared. So cosine to the fourth here isn't 1 minus u to the fourth. It's 1 minus u squared squared. It would have been worse if we made the other choice. If we had been left with a sine to the sixth here, then sine to the sixth would be 1 minus cosine squared to the third. That would be even worse than 1 minus u squared to the second. So I'm going to have to multiply this whole thing out. 1 minus u squared squared is 1 minus 2u squared plus u to the fourth times u to the seventh du, blah. It's going to be the integral of u to the seventh minus 2u to the ninth plus u to the 11th. Which is going to be, now it's just a power rule, u to the 8th over 8 minus 2u to the 10th over 10 plus u to the 12th over 12 plus c. Finally, plug back in that u is sine. So we end up with sine to the 8th of x over 8. 2 over 10 reduces to 1 over 5. So minus sine to the 10th of x over 5 plus sine to the 12th of x over 12 plus c. So that's how these sine and cosine power problems work. You're always, if they're both odd, you pick u to be the thing that's to the higher odd power. If one is odd and one is even, you pick u to be the one that's to the even power. If they're both even, you cry because you have to do the half angle formula and it just gets messy. Okay. And I think we'll talk about the secant and tangent ones next time. They're very similar in nature, but they do sometimes work a little bit differently. The idea is still the same. The idea really is you're trying to pick u to be a thing so that after you've dealt with the du part, the leftovers you can use a trig identity for. That's really kind of the whole intuition. But let us look at some integration by parts. So, integration by parts. We use it when we really kind of have a mixture of things, a mixture meaning more than one type of function, and can't just use a U substitution. So we certainly have some mixtures of things. For example, I would say that this integral of sine of root x over root x dx, I would definitely call that a mixture of things because we have a power of x, x to the 1/2, and a trig function. But this one's a U substitution. That u equal the square root of x. The derivative of the square root of x is 1 over 2 root x. So you get 2 du equals 1 over root x dx. So this problem is a U sub. And it ends up integrating as the integral of sine of u times 2 du. And so you get negative 2 cosine of square root of x. Fine. However, Not every problem is a U substitution. Here are a couple examples of things where we can't do a U sub. The integral of x e to the 2x, or the integral of, say, x squared times cosine of 3x, or the integral of x to the 4th times natural log of x, dx. All of these problems require integration by parts. And the way I kind of think about these is that x to a power, this is the algebra term, e to the something is the exponential term. X squared is, again, an algebra term. Cosine of whatever, that's a trig. X to the 4th, again, all these happen to have an algebra term. I call x to a power an algebraic term. Natural log of x is a logarithmic term. So when you have a mixture of two or more, but usually just two different types of functions, if U substitution isn't an option, which it isn't for any of these, U substitution will not work for any of these, we have to use what's called the integration by parts method. So here's where it comes from. Integration by parts really comes from the product rule. So it's kind of interesting. U substitution is really the reverse chain rule. You're undoing the chain rule when you do U substitution. Integration by parts is kind of like the reverse product rule. You're really undoing the product rule when you do integration by parts. So let me show you real quick how this works. So if I take the derivative of functions u and v, I should say the derivative of the product u times v, the derivative is u times the derivative of v, which I'm going to write as dv, plus v times the derivative of u, which I'm going to write as du. Now we're going to integrate both sides. The integral of u times v derivative, the integral of the derivative, the whole fundamental term of calculus, right? The integral and the derivative undo each other. So the integral of the derivative of u times v is just u times v. And it's equal to this. So then we're going to subtract this over to here, and we're going to say that uv minus the integral of v du is equal to the integral of u dv. So this is the formula we want to remember. I've definitely heard people say all sorts of interesting things about it. Often, I like to say it's ultra violet super voodoo. So when someone says ultraviolet super voodoo, they're talking about integration by parts. We do the ultraviolet super voodoo. So why would we do this? This seems like I haven't done anything helpful. This looks crazy. The point is this. We're trying to integrate the integral. We're trying to do the integral of u dv. And by making this change, the hope is that the integral of v du is going to be easier to integrate. That's the whole idea. Is we're going to choose a u and a dv so that this mess over here is easier. And there are ways of choosing u and dv. We typically want to choose dv to be the most complicated thing that's easy to integrate. So complicated, but easy to integrate. U, on the other hand, we often pick in this way. We often pick u to be the first thing that shows up in this acronym, light, where L stands for log, I stands for inverse trig, A stands for algebra, meaning a power of x, T stands for trig, and E stands for exponential. You're almost never letting u equal e to the something when you're doing integration by parts. So let's go back to the other side. So if I was going to try and do this first problem, x e to the 2x, I would let, well, I've got u as an algebraic thing. U is going to be x. Once you've picked u, everything else is decided. Once you picked u, dv has to be the entire rest of the thing. So u is x, dv is e to the 2x dx. Because u times dv has to be the entire integral, right? U times dv has to be the entire integral. Okay, now we're going to write down the other pieces. I need my du. Well, the derivative of x is 1, so du is 1 times dx. I need my v, and this is why we want our choice for dv to be complicated but easy to integrate, because we're going to have to integrate it. The antiderivative of e to the 2x is e to the 2x over 2. And now we're going to throw everything into the formula. The integral of u dv, in fact, let's write it out here. The integral of u dv is equal to u times v minus the integral of v du. V du. Sorry, I pointed the wrong thing. But look, this integral here is actually something we are able to integrate. You can write down here, we've got that this is now equal to x e to the 2x over 2 minus, I'm going to bring up the 1/2, the integral of e to the 2x. We know how to integrate e to the 2x. We did it in the previous step. The integral of e to the 2x is e to the 2x over 2. This ends up being x e to the 2x over 2 minus 1/2 times the integral of that, which is e to the 2x over 2 plus c. So we can leave it like this, or we can write our final answer as x e to the 2x over 2 minus e to the 2x over 4. That's the process. Are there questions about that before we do some more? One second. I'm guessing, so I saw Morgan that you wrote number 23 and 8.2. I'm guessing you meant 23 and 8.1, because 23 and 8.2 is definitely not an integration by parts problem. Maybe I'm wrong though. Anyway, let's continue with these examples and you can let me know if that's what you meant or not. So, you guys are still there, right? Like no one said anything for a while. You can all hear me, right? You're there. You're okay. Okay. Just want to make sure. Like, you guys have been quiet for a while. Okay. So, maybe, you know what? I have a different textbook. I have so here. So maybe, yeah, that's a problem. I have the because my section 8.2 is trigonometric integrals. So, okay, I'll just make something up. It's fine. Or you can write the problem if you want to, Morgan, if there's a specific problem you actually want me to do. But I think I know what you want anyway. Let's look at these problems. So for the integral of x squared cosine of 3x dx, right? Yeah. We are actually going to have to use integration by parts twice. So we might not know that yet, though, but let's start. So I'm going to start by letting, well, again, Lie8, I don't have a log, I don't have an inverse trig, but I do have an algebra term. So I'm going to let u equal x squared. dv is going to equal the rest, which is cosine of 3x dx. du is 2x dx. V is the antiderivative of cosine of 3x, which is sine of 3x divided by 3, or times 1/3. Right? Because the derivative of that would be cosine of 3x times 3, and the 3's cancel. Yeah. So this is equal to u times v so x squared times 1/3 sine of 3x minus the integral of v du, which is 1/3 sine of 3x times 2x dx. And so people kind of differ in opinion. I personally think it's a good idea to bring out the coefficients. So write this as x squared sine of 3x all over 3. I'm going to bring out the 1/3 and the 2, so I'm going to bring out the 2/3 integral of x times sine of 3x. And now I'm in the position of having to do integration by parts again, because I still have an algebra times a trig thing. So I'm going to let u equal x in my second integration by parts, my second iteration of integration by parts. And dv is going to be sine of 3x dx. Du is going to be dx. And v is going to be, okay, the antiderivative sine of 3x is negative cosine of 3x divided by 3. All right. So now what we get is, we still have all of this, right? That's still there, it didn't go away. We get x squared sine of 3x over 3 minus 2/3 times, okay, the integral of u dv is going to be uv minus the integral of v du, but it's 2/3 times all of that. So it's going to be 2/3 times all of uv minus the integral of v du. uv, so x times negative cosine of 3x over 3 minus the integral of v du, which is negative cosine of 3x over 3 dx. Whew. All right. So let's see what we've got here. I've got x squared sine of 3x over 3. I'm going to distribute this minus 2/3 to each of these terms. So minus 2/3 times this first term, minus 2/3 times the second term. Okay, so let's be extra careful here. This part I'm just going to simplify. A minus times a minus is a plus. So it's going to be plus. The denominator is 9. The numerator is 2x cosine of 3x. Now, minus a minus a minus is a minus. It's minus 2/3. Sorry, minus 2/3 times a 1/3 is minus 2/9. Integral of cosine of 3x. Right, because it's a minus 2/3 times a minus times a minus. It's a minus 2/9. Integral of cosine of 3x is, I'm going to erase because I'm out of room, is positive sine of 3x over 3. Wow, that's a lot. Would you like to see a faster way to do this problem? Of course you would. Who wouldn't want to see a faster way to do this problem? Okay. Your teachers may or may not cover this. It's not always in the book. In fact, I don't think it's in the book, but it definitely is something that I think is worthwhile. And then we'll come back to this one here. This method only works for the following 3 specific types of integration by parts problems. You have the integral of x to a power times e to the something times x, where n is a positive integer. You have the integral of x to a power times cosine of something times x. Again, n is a positive integer. Or you have the integral of x to the something times sine of ax. These 3 types of integrals, so you've got like x to the 5th times e to the x, or x cubed times cosine of 2x, or x to the 7th times sine of 1/3 x. Any problem like that, you can use the following method, which is called tabular. because you're making a table. So here's the table I'm going to make. I'm going to make a list of my u values and my dv values. And for my integral, which was the integral of x to the second sine of 3x, right? Oh, sorry, cosine of 3x. You're going to make your u table. You're going to start with your first pick for u. And then you take all the derivatives. What's the derivative of x squared? 2x. What's the derivative of 2x? 2. What's the derivative of 2? You do need to go all the way to 0. If you don't end at 0, you shouldn't be doing this method. Right? This method is only good if your u column eventually ends at 0. So here we are differentiating. On the dv side, we're going to be anti-differentiating. So my first choice for dv was cosine of 3x. The antiderivative of cosine of 3x is 1/3 sine of 3x. The antiderivative of that is negative 1/9 cosine of 3x. And the antiderivative of that is negative 1/27 sine of 3x. On this side, we are definitely anti-differentiating. Okay, here's how we get the answer. You multiply this times this and put a plus sign in front. And you don't change the sign. You multiply this times this, put a minus sign in front. You multiply this times this, put a plus sign in front. This just alternates. Plus this times this, minus this times this, plus this times this, minus this times this, plus, right, you just keep going. So check out, ow, mother son of a gun. Oof, My wife is probably laughing her ass off like that. Anyway, so, yeah. Maybe I should wear shoes in here. Ruin the carpet some more. Okay. So check out what we get. We get positive x squared times 1/3 sine of 3x minus 2x times negative 1/9 cosine of 3x plus 2 times negative 1/27 sine of 3x. Which I don't really want to write out, but I will because I like you guys. Ends up being x squared sine of 3x over 3 plus 2/9 x cosine of 3x minus 2/27 sine of 3x plus c. If you look back at our previous answer, same damn stuff. That's 2/27. So this is a really, really powerful tool if you don't want to have to do repeated integration for ones that are specifically like x to the 5th times e to the x. You could do x to the 5th times e to the x with integration by parts. You could do it 5 different iterations of integration by parts, or you could do tabular. Okay, now we're almost out of time. I feel like I should give you guys one more problem here. The problem I think someone was trying to ask about, but I'm not positive, is this problem. It's the integral of e to the x times, sure, let's do cosine of 4x dx. So specifically when you have e to the something times either sine or cosine, you have to do repeated integration by parts, and then you have to kind of, well, you have to look and see. So I typically like to let u equal the trig thing. When you have a trig, when you have a cosine times an e to the x, you can technically choose either one. I'm going to let u equal cosine of 4x. And my dv is going to be e to the x dx. My du is the derivative. It's negative sine of 4x times 4 dx. My v is just e to the x. So here's what we get. It's going to take a minute. So this thing here is equal to uv minus the integral of v du. So it's going to be e to the x times negative 4 sine of 4x dx, which I would then rewrite as e to the x cosine of 4x minus a minus is plus, we'll bring out the 4, integral of e to the x sine of 4x. And now we have to do another integration by parts. So I'm going to so here's where you have to be extra careful. You have to make the same type of choice you made the first go around. Meaning if you let u equal the trig thing, you got to let u equal the trig thing again. If you do it the other way, if you let u equal e to the x and dv equals sine of 4x, you'll undo all the work you did, and you'll get integral of e to the x cosine of 4x is equal to the integral of e to the x times cosine of 4x, which is very true and also not very useful at all. So we're going to let u equals sine of 4x. The derivative is 4 cosine of 4x. And dv again is e to the x, and v is e to the x. I forgot my du's here. dx, sorry. If you have to go, you can go. We're almost done though. So let's finish this problem. So we're going to get e to the x cosine of 4x plus 4 times the uv, which is e to the x times sine of 4x, minus the integral of v du. Now check this out. Make the integral of e to the x times 4 cosine of 4x dx. I'm going to put the 4 out in front. I'm going to get e to the x cosine of 4x. Well, that's no good. I'm back where I started with the integral of e to the x times cosine of 4x. It's actually fine. Because here's what's going to happen. And I'm going to write this and then I'll say some words. So I've got this integral, the integral of e to the x cosine of 4x dx equal to e to the x cosine of 4x plus 4 times this is 4 e to the x cosine of 4x. Sorry, sine of 4x. Apologies. And then finally, 4 times negative 4 is minus 16 e to the, integral of e to the x cosine of 4x dx. Here's what we do. We add this negative, we add 16 times the integral of e to the x cosine of 4x to both sides. So we end up getting, if I add 16 of that to 1 of that, I get 17 of my integral, or 17 times my integral, equal to this stuff. E to the x cosine of 4x plus 4 e to the x sine of 4x. And then to get my answer, I just divide both sides by 17. Okay, let's see. And that is how you integrate an e to the x times a sine or a cosine. You do integration by parts twice, and then you end up with essentially the same integral you started with. You add it over to the other side, and then divide by whatever coefficient to find your answer.